Alright, so today we're going to be doing the kth smallest element in a binary search tree. Given the root of a binary search tree and an integer k, return the kth smallest value, 1 indexed, of all the values in the node in the tree. Okay, so I picked this problem at this time because I think it's a good introduction to binary search trees, and then also a little bit about tree traversal. So a binary search tree specifically is a binary tree where the left child and all of its children are smaller than the parent. And same, the right child and all of its children are bigger than the parent. This is different from, say, having just where the left child is smaller and the right child is bigger, because if you only have that relationship go one level down, you could end up with, say, like, children of the left child way down the line being much bigger than the original parent. Okay, so we don't know how big the tree is because we're only given the root node and then the k for kth smallest. So, for example, another thing to add is that we're not guaranteed that the tree is balanced. All we know is it's a binary search tree, and whatever parent we're given, everything to the left and further down is smaller, everything to the right and further down is bigger. So we don't know how big the tree is. We don't know how balanced it is. So there's kind of 3, maybe 4-ish main common tree traversal methods. The in order is kind of left to right. Post order, reverse order would be right to left. Let's see if I can get post order, and then I actually can't remember that now, so I'm not going to talk about it. But post order would be where whatever action you take on the root, you do it after you've explored the children. So the difference in implementation is actually pretty kind of minor for all these different traversal methods. And it usually has to do with whether you do it before or after you recurse on any of the children. So it's going to be recursive to. For these kinds of problems, I like to make a separate function that does the traversal and most of the work, and then the main function just kind of kicks things off. I think it's easier to keep things straight instead of trying to remember how to adapt the main function to be exactly what you want to do. I find this is a little bit easier to reason about to start off with, so I usually go with a separate one. So void. I'm just going to call it traverse to keep typing short, but I'm going for in order traversal. So since we're going to be traversing the whole tree, that means we're looking at least O of n time. And then if we're going to do a recursive method, it's probably going to be O of n space as well, because you cannot neglect stack frames from the recursive calls. Sometimes I think you can get away with less by doing an iterative implementation instead of recursive, and generally that is going to scale better for space complexity, although in an interview setting, those are a little bit trickier to reason about. They usually have a few more lines of code, so it may still be better just to do something recursive, just to keep it smaller, faster to write, maybe a little bit easier to, well, it depends. They're easier to reason about when you're coming up with it, but maybe if you're reading it from scratch, iterative would be easier to get familiar with, looking at already written code. But I'm going to do a recursive here. So it's going to take it's got to take at least a root. And I think that might be it. So what I'm planning to do is I'm going to have some counter, because the recursive calls still need to keep track of where they are, if it's the first smallest or the second smallest or the third smallest. Yeah, so I'm just going to keep track of that outside instead of trying to pass things to each recursive call, because we're not trying to parallelize this. I have been asked a parallelizing question in a Google interview before. Needless to say, LeetCode doesn't cover that very much, and I over-focused on that, and so I didn't do super well on it. It was on, what was it? It was sorting but distributed. when you have something that's too big to fit in memory. Anyway, so this isn't going to be multi-threaded. This isn't going to be distributed, so it's okay to have this just like centralized counter to keep things simple for the example. All right, so int. I'm just going to call it kk because it's gonna start out as k, and I'm going to decrement it, and when it's 0, that's when I know I've hit the value that I want. Because it's one index, so yeah. Anyway, that's just kind of a simple way to go. K is always going to be a positive integer, so let's try that. So first of all, what do I need to do? I definitely need to call the traverse function. And I'm probably going to need some return value as well. So I could either try to reason about returning it all the way up through all of the stack frames from this recursive call, or I'm going to make another variable and just I'm going to keep track of it out there. So when whatever stack frame finds the answer, it's going to set return, and the others will just have to know, okay, by the time it gets all the way back to the top, this should have the correct value in it. And before I forget, I'm going to add a checking for edge cases, I guess. It doesn't specify if the root can be null or what should happen in that case. I'm assuming it should be 0. So if okay, so we're going to traverse, and I want to set this initial counter kk. So and then traverse, return the result. Oh my goodness. And actually, I am going to give this an initial value, just so that if it breaks and I see in debugging that this -1 returned, then I know that's why, because this the node values are non-negative integers. So if I make it negative and it returns that, then I know we actually never set that in a later stack frame. Okay, so now let's try the recursive one. It's obviously we need a base case so that it doesn't recurse forever. So if return void. Okay, so if it's not root, return void. What do we need to do? We want to do in order traversal. So that means recursing on the left child first, then doing work, then recursing on the right child. So for example, if you're looking at this, we want to, so 5, recurse on left child, 3, recurse on left child, 2, recurse on left child, 1, recurse on left child. Left child is null, so then we hit base case, return back. Do our work on 1, recurse on right child, it's null, so we go back. And then now we go back up to 2, do our work on there, and then we recurse on the right child, that's null, go back. And then we go up there, and then do our work on 3, recurse on 4, recurse on its child, it's null, 4, do work, right child, null, go back to 4. And then, so you end up going this 1, 2, 3, 4, 5, 6. So that's what the in-order traversal advantage has. And that's why we're doing in order instead of like post order or reverse order or anything, because we don't know how big the tree is. We know there's always a smallest. We know there's always a biggest, but we don't know how far from the smallest the biggest is. So if we go left, then it's always going to hit the smallest first, and then second smallest, third smallest, fourth smallest. So that's why in-order traversal is really the only viable pattern for this. All right, so left child, traverse, root, left. And then we do work. So what do we do? Decrement kk. And then we want to see if we've hit our k target value. So if kk equals 0, it's not null. I mean, the not signs, that's kind of like a universal way it'll work. Maybe writing as like equals equals 0 would be more obvious what's going on. I don't know. That's a stylistic choice. You might as well write a comment if you're trying to distinguish between those two cases. But then that gets to code readability, which does kind of matter with these interviews. So, okay, so if we've actually hit our solution, we want to set the return value and break. So return equals, and we know it's not null because we already covered that there. And then we want to specifically return. And another advantage of using this counter that's external to all of the recursive calls is that it's synced between them. So when we return from here and it goes back to its parent, that one's gonna then see. It's either gonna, if it's a left child, then it's gonna come back out of here. Oh, you know what? Okay, so I need to decide if this should be before or after. So it was gonna come back out of here, decrement. Okay. What I'm gonna do? Okay, if kk is less than or equal to 0. And the reason for that is because if it's a left child and it's coming back out, we're going to decrement the counter and then break and return. And we want its parent to see that, okay, we've already hit our value, and then it's going to skip traversing the right child. That's not going to change asymptotic runtime complexity, but it does have a significant constant factor that it reduces. So that's still important. It still makes a difference in the real world. It's still something to think about. And then we don't have to account for no longer decrementing k when we've hit our value. So I mean, there's that minor bit of work since they're all going to decrement. I suppose we could say minus equal to 1, or and then decrement after actually. So that would that reduces it by another constant factor of n because then we're no longer doing this if we hit our value. So kth smallest equals to 1 instead of 0. And then, okay, so if none of that happens, then we want to traverse the right child. Parentheses. And then implicit return void at the end. Okay. So that might be it. Let's step through an example, I guess. Okay. Okay, so I already mentioned that. Let me cover time and space complexity first. I already mentioned that time is O of n for the traversal. With O of 1 time work at each frame, at each node. Space is also O of n, stack frames. If the tree if it's completely unbalanced or linear, that's basically what that means. So for example, if 4 and 6 didn't exist, we go 5, 3, 2, 1. That's the whole dang tree on our stack frame. So that's O of n space. Sorry, each one gets its own stack frame. Anyway, all right, so example. All right, so root is 3, integer is 1. So we want the first smallest element. All right. So if the root's null, root is not null, set k equals to 1, and we traverse. All right, so starting from the root node, it's not null. All right, so we're going to call traverse on the left child. And then on that one, it's not null, so we're going to call traverse on its left child. Its left child is null, base case, return back to 1, then we do work. Kk is less than or equal to 1, so that's where we set our value. So return value is root of value, so it's 1. Then we return. All right, so we're back up to 3. At 3, we're coming out of this, so then we see that kk is less than or equal to 1. And okay. Right. Okay, yeah, there's definitely an error here. So what's going on is 3 is going to overwrite the return value, and you end up just returning the value of the parent the whole time, and that's no good. So in that case, there's a couple of options. One would be to have a traverse return a Boolean instead, and then we can see that if say this left recursion returned true or something, that means that a solution was found, and then we don't need to do the work, and then we break. So that's also an option. Oh, you know what? Yeah, that's what I'm going to do. Let's make this Boolean. Return true. Return false. And then if do I want to mess with, I could do an if there and an if there, and then to just see. Okay, what's a clean way to do this? Because this Booleans would work. It's a little messy. Maybe for the sake of time, that would be the way to go. So root. Okay, so I'm gonna say if return. Okay, so I'm only gonna set the return value if it's not already set. That's what I'm gonna do. If return is less than 0, and then I don't need to mess with Booleans. Oops. All right. So that does that another logical check. So then that's another factor of O of n total, but that doesn't change asymptotic runtime. All right. So now, okay, back to the example. If we're at 3, so it's not. So we come out of this. K is less than or equal to -1. But we see that 0 is, sorry, we see that the return value is greater than or equal to 0. So we're not going to set it, but we are going to return. And I think that solves it. And then from there, we're going to return, so exit, come back to this, return the return value. Okay, let's step through one more example, because these go kind of quick anyway, so might as well. All right, 5 at the root. And 3, so third smallest. 1, 2, want to return this basically. 5 at the root. Root is not null. Kk equals to 3. So we're going to traverse the root. It's not null. So we're going to traverse its left child. Not null. Traverse its left child. All the way down to here. Null. Back to 1. Kk is, this is not true, so we're not going to enter there. Well, we are going to decrement kk. And then we're going to traverse the right child. It's null. Go back up to 2. Coming out of there. We're going to decrement k. Go there. It's null. Back up. And then back up to 3. And then we're going to do work here. So we've decremented k twice. That means k was 3, and then it's 2, and then it's 1 coming up to here. So we are going to enter this. So the return value is still -1. So we're going to set it, and it's going to be 3, and then we're going to return. And then, okay, so then we're turning back up from 3. We're not traversing here. We're skipping that, so we're going back up to 5. 5, we're going to do work. We're going to see kk is less than or equal to 1, but the return value is set 3 currently. So we're not going to set that, we're just going to return. So now we're back up to here. Coming out of traverse, return value is still 3, it has not been changed, and then we're going to return that. Okay, I think that's good. Let's give it a run, check for syntax errors. Traverse. Ah, typo. All right, okay, so there, case 2. Let's try it. And golden. Okay, those don't matter, but we're gonna check it off our list. Kth smallest element. Done. Thanks.